Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, RCADT, presents the conference. Kalman Filter and Neural Nets. Real-time predictive artificial intelligence, hybrid, parallel, and distributed. Uncertainty dynamic systems. Modeling. Uncertainty dynamic systems. Uncertainty dynamic models of uncertainty dynamic systems. Let's define a data-driven probabilistic dynamic model as one that can adapt to the variations in system behavior that are represented in the stochastic process sample. There are multiple alternatives to address the problem. Statistical parameters associated with a predefined mathematical, algebraic structure that varies over time. Assembly of a dynamic model based on multiple statistical models whose weighting factor, usually the probability to be the true model, is determined based on the sample being processed. Use of state estimation methodologies. Mixing several methodologies. Mathematical methodologies. Probabilistic classic methodologies. Bayesian models. State estimation. Markov models. Statistical model. Set of algebraic equations, assumed by the mathematical modeler, that explain the process from the observed data. Univariate models, linear and nonlinear regression, box and Jenkins models, Garch models, SR-Max Garch models. Multivariate models. Simultaneous equations. The White Paper. Theory of dynamic systems under uncertainty. Presents part of the theory of this presentation. Kalman filtering and neural nets. The integration of Kalman filtering, KF, and neural networks, NN, represents a powerful hybrid approach in modern artificial intelligence, combining the mathematical rigor of control theory with the flexible pattern recognition of deep learning. The integration of neural networks, NN, and Kalman filter, KF, represents one of the most advanced frontiers in modern artificial intelligence. The combination of these technologies makes it possible to overcome the individual limitations of each one, the linearity of the KF and the lack of interpretability of the NN. The integration of neural networks, NN, and Kalman filter, KF, represents one of the most advanced frontiers in modern artificial intelligence. The combination of these technologies makes it possible to overcome the individual limitations of each one, the linearity of the KF and the lack of interpretability of the NN. Core synergies. The relationship between these two technologies usually falls into one of three categories. Kalman filters for training neural networks, the extended Kalman filter, EKF, and the decoupled EKF, DEKF, can be used as alternatives to traditional backpropagation for training NN, leading to faster convergence and better noise handling in dynamic and/or chaotic environments. Neural networks that help Kalman filters. Deep learning improves the weaknesses of the KF standard, that requires an accurate linear model to function optimally. Parameter adjustment. NNs can learn to predict in real time the optimal matrices, process noise and measurement noise. Error compensation. NNs can predict unmodeled errors, nonlinearities that the KF physical model cannot explain. Hybrid architectures. Recent innovations such as Kalman Net incorporate recurring NN directly into the KF flow. This allows the system to learn complex dynamics from the data, while maintaining the interpretability and efficiency of the standard KF. Key benefits. Robustness in uncertainty. Although maintenance networks can struggle with noisy data and forgetting in dynamic environments, the KF provides a recursive framework that naturally manages uncertainty. Real-time performance. Hybrid models are typically highly efficient, making them ideal for high-definition applications in robotics, autonomous navigation, and financial forecasting. Reduced data requirements. Leveraging the KF structural knowledge, hybrid models typically require less training data than purely data-driven NNs. Kalman Net, neural network-aided Kalman filtering. This section is based on the paper Kalman Net, neural network-aided Kalman filtering for partially known dynamics. The estimation of the real-time state of dynamical systems is a fundamental task in the processing and control of signals, for systems well represented by a fully known linear Gaussian distribution. The Kalman filter, KF, is an optimal low-complexity solution. However, Both the linearity of the underlying state estimation (SE) model and its accurate knowledge are often not found in practice. KalmanNet is a real-time state estimator that learns by incorporating into the KF stream a module dedicated to a recurring neural network, maintaining data efficiency and algorithm interpretability, while implicitly learning complex dynamics from the data. Numerically, KalmanNet overcomes the nonlinearities and mismatches of classical models, overcoming classical filtering. It is a method that operates both with mismatched domains and with a precise domain of knowledge. The main features of KalmanNet are summarized as follows. KalmanNet is a low-complexity, data-efficient, real-time deep neural networks (DNN) assisted real-time state estimator. KalmanNet is based on the principles of the Kalman Filter (KF), incorporating partial knowledge of the underlying state space (SS) domain into its operation. KalmanNet avoids the dependence of the KF on the knowledge of noise statistics, thus avoiding the problematic numerical inversions of matrices involved in the equations, overcoming the need for solutions adapted for nonlinear systems, for example, approaches to handle nonlinearities such as the extended Kalman Filter, EKF. KalmanNet performs data departing in a way that is sequence length invariant, based on an efficient supervised training scheme, allowing to infer arbitrarily long trajectories, while only training using short trajectories. KalmanNet was evaluated on linear and nonlinear SS models and was shown to converge much faster compared to purely data-driven (DD) architectures, while outperforming EKF when faced with dominant model mismatches and nonlinearities. Mismatched domains and with a precise domain of knowledge. Although the original KF assumes linear state space (SS) models, many problems encountered in practice are governed by nonlinear dynamical equations. Therefore, after the introduction of KF, nonlinear variations of KF were proposed, such as the extended Kalman Filter, EKF, and the unscented Kalman Filter, UKF. These variations for nonlinear SS models are not optimal and suffer severe degradation in the face of strong nonlinearities. KF and its variants are model-based algorithms, MBs, that is, they are based on a precise knowledge of the underlying SS model. The performance of MB methods depends on the validity of this domain knowledge. In practice, the underlying dynamics are often complex, nonlinear, and difficult to accurately estimate and characterize as a manageable SS model. Recent years have seen remarkable success of deep neural networks, DNNs, in real-world applications. These data-driven, DD, models can capture the subtleties of the true generative process, and to replace the need to explicitly characterize the domain of interest. Therefore, an alternative strategy for implementing state estimation is to learn this task from data using deep learning. The DNNs can be trained comprehensively, and model independently, from a large amount of data to capture complex dynamics, including models of recurrent neural networks, RNNs, such as long short-term memory, LSTM, and gated recurrent unit, GRU, cells. Although these DD architectures work very well in unstructured environments, they lack the interpretability of MB methods and tend to require many trainable parameters even for seemingly simple sequence models. These constraints limit the application of highly parameterized deep models for real-time state estimation in hardware-constrained mobile device embedded applications, such as drones and vehicle systems. The main contributions of KalmanNet are summarized as follows. KalmanNet is an interpretable, low-complexity, and data-efficient DNN-assisted real-time state estimator. KalmanNet is based on KF, incorporating domain knowledge of the SS model. By learning the Kalman gain matrix, KG, KalmanNet avoids KF's dependence on knowledge of underlying noise probabilities, avoiding numerical matrix inversions, implied in KF equations, and avoiding the need for solutions adapted for nonlinear systems, such as the EKF. KalmanNet learns how to perform KF from data in a sequence-invariant manner. Specifically, it has a supervised training scheme, which allows inferring arbitrarily long trajectories while only training using short trajectories. KalmanNet has been shown to converge much faster compared to pure DD architectures, while outperforming EKF when faced with dominant model mismatches and nonlinearities. The figure shows the extended Kalman Filter, EKF, block diagram. EKF linearizes the SS model, and it is a two-step procedure, prediction and update, where in each step EKF computes the first and second order. Statistical moments. Z-1 is the unit delay. The figure shows the block diagram of Kalman Net. Kalman Net is based on a hybrid and interpretable data architecture for real-time state estimation in nonlinear dynamic systems, with partial knowledge of the stochastic domain. The covariance matrices Q and R are not available. These missing statistical moments are only used to calculate the Kalman gain matrix, Kg. Kalman Net combines KF with a recurrent neural network, RNN, to address model mismatches and nonlinearities. Kalman Net learns Kg from data and combines it with the global KF flow. The prediction step is the same as in the EKF, except that only first-order statistical moments are predicted. The update step uses the current YT observation, as in EKF. However, unlike KF, here the calculation of the Kg is not given explicitly but is obtained from data using the RNN. RNN's inherent memory makes it possible to implicitly track second-order statistical moments, without requiring knowledge of the underlying noise statistics. Designing an RNN to learn how to compute the Kg as part of an overall KF flow requires answers to three key questions. From which input signals will the network learn the Kg? What should be the architecture of the internal RNN? How will this network be trained from data? The figure shows the Kalman Net RNN block diagram, architecture number 1. Kalman Net uses a single gated recurrent unit, GRU, layer, but one can also utilize multiple layers to increase the capacity and abstractness of the network. Therefore, the following quantities which are related to the unknown statistical relationship of the SS model can be used as input features to the RNN. F1 the observation difference. F2 the innovation difference. F3 the forward evolution difference. This quantity represents the difference between two consecutive posterior state estimates. F4 the forward update difference. This quantity represents the difference between the posterior state estimate to the prior state estimate. In this illustration, the input features are F2 and F4. The figure shows the RNN block diagram of Kalman Net, architecture number 2. The second architecture is more directly oriented to the formulation of the SS model and the operation of the EKF compared to the simpler architecture of the first. Therefore, the second architecture provides less abstraction. It is expected to be more constrained in the family of mappings it can learn compared to the first, and as a result it also requires the training of fewer parameters. As shown by numerical evaluations, these two architectures achieve a similar performance in mean square error, MSE. In most numerical studies the first architecture is simpler, while the second is used in the experimental study that considers the follow-up of the Lorentz attractor. An extensive numerical study of Kalman Net was conducted. A. Neural model selection. Kalman Net was evaluated and the Kalman Net architecture was confirmed with the use of RNN for end-to-end state estimation. B. Synthetic linear model. The linear SS of models in which KF is known to minimize MSE was considered. Kalman Net was shown to match the KF and outperform it in the presence of a mismatched model. C. Synthetic nonlinear model. Nonlinear SS synthetic models were considered, where the EKF is the reference benchmark. It was shown that Kalman Net can achieve a better MSE. D. Lorentz attractor. Kalman Net was evaluated in real time following the Lorentz attractor, which is a nonlinear system with chaotic behavior. Concrete benefits were evaluated by following a chaotic challenging system. E. Real-world dynamics. The latest study considers the localization in real-world dynamics based on Michigan's NCLT dataset, where was demonstrated Kalman Net's ability to achieve better real-time capability. Throughout the numerical study, and unless stated otherwise, in the experiments involving synthetic data, the SS model is generated using diagonal noise covariance matrices. In our experimental study we consider following configurations of Kalman Net. C1, Kalman Net architecture number 1 with input features F2, F4 and with training algorithm V3, C2, Kalman Net architecture number 1 with input features F2, F4 and with training algorithm V1 C3, Kalman Net architecture number 1 with input features F1, F3, F4, and with training algorithm V2. C4, Kalman Net Architecture Number 2 with all input features, and with training algorithm V1. In all our experiments Kalman Net was trained using the Atom Optimizer, published by Kingma and Ba, Atom, a method for stochastic optimization. For this setup, Kalman Net with setting C1 was compared with two RNN-based architectures of similar capacity applied for end-to-end state estimation. Vanilla RNN directly maps the observed YT to an estimate of the state XT, and MBRNN imitates the Kalman filtering operation by first recovering using domain knowledge, and then uses the RNN to estimate an increment from the prior to posterior state variables. All RNNs utilize the same architecture as in Kalman Net with a single GRU layer and the same learning hyperparameters. The results, summarized in the table, show that Kalman Net maintains achieving the MMSE, implying that it learned to carry out Kalman filtering. The MBRNN and vanilla RNN are more than 50 decibel from the MMSE, implying that their learning is not transferable and that they do not learn to implement Kalman filtering. The figure shows the learning curves for data-driven (DD) state estimation. The learning curves show how each of the key design considerations of Kalman Net affects the learning curve. The incorporation of the SS model allows the RNN-MB to outperform the vanilla RNN, although both converge slowly and fail to reach the MMSE. Using different sequences as input significantly improves the convergence rate of the MBRNN, indicating the benefits of using difference features, and learning is further enhanced by using the RNN to retrieve KG as part of the KF flow, as Kalman Net does, rather than directly estimating the state variables. In this experiment, the pre-trained models were tested on trajectories of the same length they were trained on t=20. To further evaluate the advantages of Kalman Net, it was checked whether its learning is transferable. Specifically, the pre-trained models were tested using trajectories with different initial conditions and in longer trajectories than those that were trained, t=200. The figure shows the linear SS model. To avoid overlaps, an MSE offset was added in the legend for each curve. A. Full information, Kalman Net converges to MSE. B. Partial information, Kalman Net outperforms KF by 3 decibel. Kalman Net was shown to match the KF and outperform it in the presence of a mismatched model. The figure shows the nonlinear SS model. It was shown that Kalman Net can achieve a better MSE than EKF with full and partial information. The Lorentz attractor is a set of chaotic solutions for a system of differential equations that model atmospheric convection. It became famous for the butterfly effect, where small initial variations produce drastically different results, and for its visual shape, reminiscent of a butterfly's wings. A chaotic system is a deterministic dynamic system that, despite following precise laws, exhibits behavior that appears random and is extremely difficult to predict in the long term. The characteristic that best defines these systems is their extreme sensitivity to initial conditions. The Lorentz attractor is chosen because it demonstrates the task of online tracking a highly nonlinear trajectory, and it also demonstrates a real-world practical challenge of handling mismatches due to sampling a continuous time process into discrete time. The figure shows the Lorentz attractor with full information. Kalman Net is trained on short trajectories of length t=30, using the C3 setting, figure A, at left side. Despite being trained in short trajectories, empirically Kalman Net achieves excellent MSE performance. By increasing the path length to t=2000, right side, the performance is still higher. When comparing, applying the EKF with the complete information, the model achieves unstable performance, with MSE values exceeding 30 decibel. To stabilize the EKF, a grid search was performed using the available dataset to optimize the Q-noise process used by the filter. The results of the MSE represented in Figure B are those achieved by the EKF after this optimization. We observe in such scenarios, where there is no model mismatch, that the EKF and Kalman Net achieve roughly the same MSE, while the latter does not require knowledge of the noise statistics. The figure shows the Lorentz attractor, with partial information, with state evolution mismatch, and t=2000. For the mismatch of evolution of states, both Kalman Net and EKF operate with a rough approximation of the evolutionary dynamics obtained by calculating with JMDL =2, while the data are generated with an expansion of the Taylor series of the order JMDL equal to 5. The results show that Kalman Net, with the C4 fit, learns to partially overcome this model mismatch, outperforming the EKF that operates with the same partial information level. The resulting MSE values of Kalman Net with configuration C4 compared with the EKF and the PF are reported in Table 3. The results demonstrate that Kalman Net overcomes the mismatch induced by representing a continuous time SS model in discrete time, achieving a substantial processing gain over the alternatives due to its learning capabilities. In Table 4, Kalman Net infers faster than the classical methods, thanks to the highly efficient neural network computations and the lack of matrix inversions. Among the different architectures of Kalman Net, architecture number 2 is noted to be slightly faster than architecture number 1 as it uses less parameters. The figure shows the Lorentz attractor, with partial information and with observation mismatch and t equal 2000. The figure shows the Lorentz attractor with full information. Tests were carried out with 3 filters: extended Kalman filter, particle filter, and Kalman Net. The image includes the true trajectory and the observation. The figure shows the Lorentz attractor with full information. The figure shows how this gain translates into improved trajectory tracking. It shows that in such nonlinear setups, the suboptimal model approaches operating with full information of the SS model are substantially outperformed by Kalman Net. Real-world dynamics is the latest study, which analyzes dynamic localization based on Michigan's NCLT dataset. This dataset is comprised of different labeled trajectories, each one contains noisy sensor readings, like GPS and odometer, and the ground truth location of a moving Segway robot. Given these noisy readings, the goal of the tracking algorithm is to localize the Segway from the raw measurements at any given time. The vanilla RNN, which is agnostic of the motion model, fails to localize. The figure demonstrates the superiority of Kalman Net for such scenarios. EKF blindly follows the trajectory of the odometer and is unable to justify the drift, producing an estimate very similar to or even worse than the integrated speed. Kalman Net overcomes errors induced by noisy odometer observations and provides more accurate real-time locations, demonstrating the advantages of combining KF model-based inference with embedded DD modules for real-world applications. NKF, neuron-based Kalman filter. With nonlinear autoregressive model. A neuron-based Kalman filter with nonlinear autoregressive model. It is the key paper in this section. The control effect of various smart terminals is affected by the accuracy of data detection. The filtering method has been the typical soft computing method, used to promote the level of detection. Due to the difficult recognition of the system, and the empirical estimation of parameters, a Kalman filter based on neural networks is proposed, according to the following process. An improved Kalman filter was designed, in which neural networks are introduced. The functions of neural networks were excavated with a nonlinear autoregressive model. Neural units optimize the filtering process to reduce the effect of impractical system model and hypothetical parameters. An adaptive filtering algorithm based on the modified Kalman filter is proposed. The filter was verified with simulation signals and practical measurements. The results showed that the filter is effective in removing noise within the soft computing solution. The Kalman filter, KF, provides a framework for filtering noise and estimating the state of the system. The components of KF can be divided into 2 categories: models and intermediate variables. The models describe the dynamical equation and the equation of measurement. Intermediate variables have a serious influence on the filtering results, but in practice they are difficult to determine, since normally they are not known a priori. The noise matrices A, Q and R, expressed as matrix A, noise variance in the equation of state, matrix Q, noise variance in measurement, and matrix R, covariance between the dynamic equation and the equation of measurement. The effect of noise variances is expressed in the filter gain matrix, K or Kg, and determines the estimated result as an important weight. The neurons are integrated into the Kalman filter and help optimize the filtering process with the limited information that exists. In neural optimization thinking, The relationship between filtering results and intermediate variables should be explored. The figure shows the structure of the neuron-based Kalman filter, NKF, which is composed of first neuron unit to predict the state variables, and second neuron unit to estimate the final state. The idea is to use the hybrid filter to estimate the K-matrix. KF and artificial neural networks, ANN, are combined in a tight pattern, in which ANN is applied during the internal filtering procedure. Lee et al. Proved that the gain of the extended Kalman filter, EKF, is modified with erroneous measurements, which reduces the accuracy of the gain. Therefore they used ANN to train the gain with the input of the measurement, estimation and error, and it increased the accuracy. In NKF the critical components are the neural units that help to determine the intermediate variables to support the final filtering result. In reference to the analysis of the two units, the two functions must fit the nonlinear relationship in multiple variables and explore the characteristics of the time series of data. With both aspects, the nonlinear autoregressive model with exogenous input, NARX, may be the appropriate solution, since it is effective in the reconstruction of nonlinear systems. NARX belongs to a recurrent neural network, as it has a high learning efficiency with gradient descent. The figure shows the structure of NARX. A nonlinear autoregressive network with exogenous inputs, NARX, consists of the input layer, hidden layer, and output layer. The transfer function of NARX is like the backpropagation neural network, and a one-hidden layer network. Figure shows the overall architecture of a NARX neural network. The figure shows the structures of the two neural units in the proposed KF. For neural units, the scale can be determined with the traditional empirical mode. The number of hidden layers is set according to the number of input and output variables. The number of hidden nodes must be determined based on the equations and can be adjusted in the training of the network, following its performance. The figure shows the algorithm flow of the adaptive NKF. The input, output, and internal structure of neural units are designed to improve filtering. NKF is based on enhanced KF, in which neural units are first trained and then applied to the filter. The algorithm consists of two parts, namely the training process on the left, and the filtering process on the right. The image presents the description of the adaptive filtering algorithm, based on the improved Kalman filter, in which neural units are first trained and then applied to the filter. NKF, neuron-based Kalman filter. Case, following a robot. In 2019, the simulation and practice experiments was conducted to test the filter proposed. In the simulation, different noises are generated to simulate the complex noises in the sensors. To test the quality of the results of three state estimation models were compared. KF, standard Kalman filter. IAKF, improvement adaptive Kalman filter, and NKF, neuron-based Kalman filter. The experiment corresponds to estimating the trajectory of the wheeled robot on a playground. The robot started from the top right corner and ended at the same point. A low-cost GPS receiver is used to obtain location information, longitude and latitude. Experiments were carried out with two samples, one white noise, signal 1, and the other colored noise, signal 2. Figure shows the trajectory of the wheeled robot. The image on the left is calculated using an exact mathematical formula, and the image on the right shows the results of filtering on the x-axis and y-axis. The common noises in sensors are the white noise and color noise. The signals with the two kinds of noises are generated in the simulation. The first set is the approximately linear noises, and the second one is the sinusoidal noises, corresponding to the white noise and color noise, respectively. In the simulation, the sampling interval is 0.02 seconds. The numbers of signal samples are all 2000, and the sampling time is the 40 seconds. Simulation 2 signals are shown in the figure. The average true values of signal 1 and signal 2 are 0. For neurounits, the first 70% of the data is set as training data and the rest is used for validation. In the context of the two neural units, the number of hidden nodes is set to 3 and 6, respectively. Other settings are also tested for optimal performance. The results of the NARCS training are shown in the figure. Filtering the results of the simulation signals, result of the x-axis. For signals that correspond to white noise, the results are relatively similar. NKF performs slightly better than the others. The figure shows the result of signal 2. Filtering the results of simulation signals, y-axis result. For the second set, color noise, the results show distinguishable trends. KF's results fluctuate sharply and diverge in the last period. IACF and NKF can track signals more closely, and NKF is the most effective. The figure shows the displacement in x-axis. For signals that correspond to white noise, NKF performs slightly better than the others. The trend is evident in the criteria for evaluating the mean average error, MAE. NKFs may decreased by 45.72% compared to KF and 21.41% compared to IACF. RMSE shows root mean squared error. The RMSE of NKF decreases by 45.23% of KF and 20.91% of IACF. The error reduction of the second set is greater than the first. The figure shows the whole trajectory in the XY plane. The results show intuitively the small differences in the filtering results, and it is because the difference is in the order of magnitudes less than 1 meter. The differences are more evident in the absolute errors. The filtering results with all three methods are like the pattern of the second set of signals in the simulation. This is because the noises are correlated. KF fails in the practical system, because KF is oriented to linear systems and not to nonlinear systems, which is the case with the experiment. That explains its lousy relative performance. Its results are unstable and diverge over time. NKF performs better than the other methods, in different historical periods at the beginning. The general trend is consistent in the x and y axes of the three methods. Neural network-based Kalman filters in oceanography. As a case study, the spatiotemporal interpolation of SST fields derived from satellites associated with infrared sensors is considered, which can imply high data loss rates, typically between 50 and 90%. Neural network-based Kalman filters for the spatiotemporal interpolation of satellite-derived sea surface temperature. It is the key paper in this section. Predicting and reconstructing ocean dynamics is a crucial challenge. Although strategies guided by mathematical models remain the leading approaches in the reconstruction of spatiotemporal dynamics, the increasing availability of data collections has increased their relevance as computationally efficient representations. From this point of view, recent advances in machine learning, especially in neural networks and deep learning, generate a new infrastructure for dynamic modeling and interpolation within a data-driven framework. This work presents a neural network-based Kalman filter for the spatiotemporal interpolation of sea surface dynamics. This approach can be considered an alternative to classic filtering schemes such as the ensemble Kalman filter, NKF. Overall, the key features of the proposed approach are twofold. An architecture for the stochastic representation of two-dimensional, 2D, geophysical dynamics based on neural networks is proposed. A parametric filtering scheme associated with the Kalman filter is used for a computationally efficient spatiotemporal interpolation of sea surface temperature, SST, fields. A case study is presented off the coast of South Africa. Numerical experiments report significant improvements in reconstruction performance compared to operational and state-of-the-art schemes. Predicting and reconstructing ocean dynamics is a crucial challenge. Although strategies guided by mathematical models remain the leading approaches in the reconstruction of spatiotemporal dynamics, the increasing availability of data collections has increased their relevance as computationally efficient representations. From this point of view, recent advances in machine learning, especially in neural networks and deep learning, generate a new infrastructure for dynamic modeling and interpolation within a data-driven framework. This work presents a neural network-based Kalman filter for the spatiotemporal interpolation of sea surface dynamics. This approach can be considered an alternative to classic filtering schemes such as the ensemble Kalman filter, NKF. Overall, the key features of the proposed approach are twofold. An architecture for the stochastic representation of two-dimensional, 2D, geophysical dynamics based on neural networks is proposed. A parametric filtering scheme associated with the Kalman filter is used for a computationally efficient spatiotemporal interpolation of sea surface temperature, SST, fields. A case study is presented off the coast of South Africa. Numerical experiments report significant improvements in reconstruction performance compared to operational and state-of-the-art schemes. The figure shows the neural network-based representation of a spatiotemporal dynamical system. The input xt is first decomposed into p-square patches, each patch is then propagated using its associate local stochastic dynamical models. The mean component of the output xt plus 1 is reconstructed by injecting the forecasted patches into the reconstruction model. The block diagonal covariance matrix is formed by the collection of the patch-level covariances. The figure shows the algorithm 1-patch-based NNKF reconstruction. Given a trained patch-based NN representation, the associated Kalman-like filtering procedure is derived. The figure shows the selected patches on the high-resolution component of the sea surface temperature data, SST. The SST map corresponds to July 19, 2015. Experimental setting. The considered parameter setting is as follows. Optimal interpolation, OI. A Gaussian core with a spatial correlation length of 100 km and a temporal resolution of 3 days is used. These parameters are empirically adjusted for the dataset under consideration using a cross-validation experiment. Analog data assimilation, local analog forecast, LOF-NKF, and global analog forecast, GAF-NKF. The acronym NKF stands for Ensemble Kalman Filter. 20 patches and the 50-dimensional EOF decomposition with a 10-pixel overlap are considered. PB-VE-DYNAV-based reconstruction, state-of-the-art interpolation scheme based on projecting our observations with missing data based on EOF. The SST field is decomposed as in the previous case. Each patch is reconstructed using the VE-DYNAV method. Table 2 presents the forecasting experiment for several prediction time steps. Table 3 presents the interpolation experiment, reconstruction correlation coefficient and RMSE over the SST time series and their gradient. It reveals the importance of the EOF-based parameterization of the NN-based covariance model in the improvement of interpolation results. The PB-NNKF EOF scheme outperforms both analog forecasting operators, in terms of predictions one step ahead, that suggest better assimilation on a global scale, especially for missing data areas. The figure shows the reconstruction and gradient RMSE time series for the selected models. The neural nets-based scheme, PB-NNKF EOF, leads to significant improvements over the optimal interpolation and PB-VE-DYNAV schemes in terms of RMSE and correlation coefficients for both SST and its gradient, with a relative improvement of RMSE of more than 50% for missing data areas for SST and its gradient, 40%. This gain clearly emphasizes the fine-scale restructuring that is not solved with OI and DYNAV schemes that rely solely on data to interpolate the SST field. Therefore, when provided with observations with a high rate of missing data, these techniques can only go up horizontal scales up to about 100 km. In contrast, the data-driven model combines observations and results to reconstruct the SST field. The analysis of the spectral signatures leads to similar conclusions, with the PB-NNKF EOF scheme being the only one to recover significant energy level up to 50 km. Qualitative analysis of the proposed schemes. The figure shows the interpolation of the SST field on July 19, 2015, first row, the reference SST, its gradient and the observation with missing data, here, 82% of missing data, second row, interpolation results using respectively OI, PB-VE-DYNAV, GAF-NKF, LOF-NKF, PB-NNNKF, PB-NNNKF EOF, third row, gradient of the reconstructed fields. The visual analysis of the reconstructed SST gradient fields emphasize the relevance of PB-NNKF EOF scheme to reconstruct fine-scale details. While OI and PB-VE-DYNAV schemes tend to smooth out fine-scale patterns, the analog data assimilation may not account appropriately for patch boundaries. This typically requires an empirical post-processing step. The figure shows the radially averaged power spectral density of the interpolated SST fields with respect to the reference SST. The analysis of the spectral signatures leads to similar conclusions, with the PB and NKF-EOF scheme being the only one to recover significant energy level up to 50 km. Tribute to Hernando Duran Castro, my master's professor, in 1975, at the Universidad de los Andes. Nothing is necessary, nothing is enough, everything is useful. Always must learn. I added. May he rest in peace. Thank you for your attention.